6:30, so we're going to talk about the generator effect today, or in this video. The last video we talked about the motor effect, where that took electric energy and changed it into kinetic energy for us by using permanent magnets and current in wires. And those current in wires produce a force, magnetic force. But now what we're going to do now is we're going to actually apply a force to, say, that armature that was spinning around. So we make it spin within a magnetic field. And then hopefully we can create electrical energy. So two scientists that discovered this and that proved it as well as Faraday and Henry, they thought that since Ørsted said that current can produce a magnetic force, why can't a force produce current? So they thought there was symmetry in the world, and there was. The reason that I have a picture of a plane here and a satellite is because this idea of moving something through a magnetic field by forcing it to move through a magnetic field to produce current is very important for commercial applications such as this. So I'm going to, at the bottom of this page here, I'm going to draw this a plane. So what I'm going to do is I'm going to draw a top-down plane. Here's the Earth, okay. I'm going to draw a top-down plane right here. Here's my plane. Right? It's flying this way. Right? So it's flying across the Earth this way. Now, what I want out of this picture is I want to know this picture, the orientation of this is I want this to be him flying over the North Pole. Okay? The North Pole, the geographical North Pole. And what we know about the geographical North Pole is technically pretty close in proximity to where the magnetic south pole of our planet is. So there's going to be field lines, magnetic field lines, that's going to be traveling across the surface of the planet from our geographical south pole, which is the magnetic north, because that's where the lines come out of. And they're going to come out, then they're going to land somewhere around our North Pole. So our North Pole is technically the magnetic South Pole. So the magnetic field lines at the North Pole, and let's just say this is the North Pole, are actually going downwards. Okay, so if you're standing on the geographical North Pole or somewhere around there, the field lines are generally going pretty down. The compasses won't point that way, so you gotta think if you have a three-dimensional compass, they would point downwards at that point. So we have these field lines pointing down here. Yeah, so I'm going to zoom into this picture. Yeah. So with this plane traveling sideways, so this plane is actually moving this way. That's the speed of this plane. We got the magnetic field lines going down. Now, if I were to draw, or think of my hand rule, so what's actually happening is I'm moving this object. And inside this object, there's a bunch of electrons because it's a conducting material. It's probably made out of aluminium or some steel in there. Light materials and stuff. But as I move it, so as I'm forcing it to move, I'm moving those electrons as well. So this is being pushed along by the thrusters. The thrusters push the plane along. The plane pushes the electrons along with it. So the electrons are now moving this direction. So I could say that my electrons are actually moving this way. Let's change that color to this one. All right? So my electrons are moving this way. That's a pretty ugly electron. Let's redraw my electron here. Oh. So my electrons are moving that way. All right, so I'm going to use my hand rule now. So I'm going to pull up my left hand, put my thumb in the direction of electrons, put my fingers in the direction of the magnetic field. I'm going to realize that, oh, all the electrons, even though I'm moving them to the right, even though I'm moving them this way, they're getting forced downwards as well. So all the electrons that are in this plane, all over the place here, they're all going to move downwards, and the electrons are going to kind of bunch up on the bottom down here. So all my electrons are here. It's going to leave some positives up here. Remember, it's not going to move the positive ups. If the positives were free to move, you'd use your right hand, and you realize that if I did that, they'd all be forced upwards, but it's just going to leave the positives behind. So this side of the wing becomes positively charged. This side of the wing becomes negatively charged. Now, this is just a parallel plate system. So right now what we would have is an electric field. So there would be an electric field between the two wings. And electric fields are going to cause some problems with electrical devices, such as the instruments in the cockpit, any computers and laptops that are running within the plane as well. Now, the airlines and the engineers have devised some situations to try to reduce this voltage, reduce this electrical field that would be produced between the two wings of this situation. They would probably attach some kind of electron pump and another battery or something to kind of force those electrons back to where they were, to keep the electrons from moving as well. But they had to account for this, and satellites had to account for this too, because they're moving much faster, and they're still moving through our magnetic field, because the magnetic field is all around our planet. So as they move through the magnetic field, electrons are going to bunch up on certain sides of this. So it's going to become positive. There's going to be a voltage difference there. And some engineers actually take advantage of this. They actually use it to help us power certain things as things move around the planet as well. So this idea that you physically move something and it would move the electrons as well is what we call the generator effect. So we are generating electron or electricity in this situation. Now, it's not very useful in a plane because the electrons would go down and they would stop. They wouldn't complete a circuit or anything. But if you could get it to complete the circuit, that'd be great. So this idea of moving wire, moving metal through a magnetic field produces this electric current. You can see in this little example here, it works the same way. Rather than moving wire through a magnetic field, you can actually move a magnet around wires. And when I move the magnet around the wires, you can see that there's current being produced, which lights up this light bulb, which gives us a little bit of voltage on each side there. Now you notice that if I don't do anything, there's no current. So it has to be a changing magnetic field. So by moving the wires in the magnetic field, you're changing the magnetic field around the wires. Here, you're just changing the magnetic field around the wires by moving the magnet itself. And you can see that you're just worried about what's pretty much what's inside here. So there's a high density of magnetic fields here. When I move it away, there's a lower density. But when I moved it, you saw the light bulb go. So right now I have a low density. If I move it, it's going to have a high density. You're going to see it move, right? So you're going to see the current go through. And if the faster you go, the faster the change, the more voltage you're going to get. The slower the change, the less voltage you'll get. You can move it around on the outside. You can see that that works as well, right? As long as you're changing the magnetic field within the rings around the wire, you're going to produce current. So if I could just pick up the wire and move that around the magnet, it would work the same way. We're going to talk about the direction. What is the direction of the current that's inside this coil when we talk about the next law called Lenz's law? That's a totally different story at this point. That's the next video. Okay. So when you're producing electricity using physical force and applied force by moving the wire, we could still just use the left-hand rule to determine what's the direction of the current that's in the wire. If it's just a straight line, it gets a little bit trickier when you have that coiled wire in there, but we'll deal with that coiled wire when we get to the next law. Let's look at this straight wire that we have here. So we take this wire, and we physically just take this wire and just pull it up. So we have this wire right here, and we just pull it upwards. We apply some kind of force. Maybe it's a water wheel has a waterfall pushing down, spinning that around. So something's pushing it along. And when I push that along, it could be steam as well in a turbine. So when I push that along, I apply a force this way. So I'm applying a force. I'm going to apply a force that way. It's going to change the speed. So the electrons are now moving this way. You can see here, I put a little V here. So these electrons, there's a lot of electrons in here. All of these electrons are moving upwards now. Okay? So since they're moving upwards, because I'm moving them upwards, I'm going to put my thumb in that direction. So I'm going to use my left hand because it's negatively charged. Then I can put my fingers in the direction of the magnetic field. You can see in the picture that my magnetic field is going from north to south, like it always does. Right? So I'm going to put my fingers in that direction, my thumb upwards. You notice the palm is coming out of the page. So my palm is coming out of the page, so therefore the force is coming out of the page. So all these electrons, even though I force them upwards, are also going to be, so I force electrons upwards, they're also going to be forced out of the page. So they're going to move in that direction too. They're going to accelerate in that direction, if they can. If there was no direction like wire there or additional wire, it would just stop and push the wire. But they're going to move through the wire in that direction. So that's going to be their new speed. So they're going to go this way. So my electrons are going to flow around this system. All right, it's going to push one electron, then another electron, another electron. They're not going to move very fast. The drift speed of electrons in current and wires are really small. But there's enough electrons in there to create enough current that we need. Yeah. Now, the next law, which I'm going to talk about, is Lenz's law. And what Lenz's law is that when these electrons start moving, so the current is now produced. This new current that's produced is called the induced current. So we just induced a current by moving the wire within a magnetic field. So the current is now being produced. Now the current is being produced in this wire. It's actually moving this way now. So my current is moving this way. It used to be moving up, right? It's still kind of moving up because we are moving the wire still up, but now they're moving as well out of the page. They're moving out of the page. Now, because they're moving out of the page, I can also think about now my thumb going that direction as well. So my thumb is going that direction, and my field is still going the same way from north to south. My palm is now going downwards. So all these electrons that are in here that are moving through this wire are also experiencing, a magnetic force downwards. Now I drew them really small. Now all the electrons are all getting forced, as long as they're moving through the magnetic field in that direction, so they're coming out of the page, they're all going to get forced downwards. So their experience of force downwards, I'm applying a force upwards to make them move that way, and then they apply a force back down. So what they're actually doing is they're adding resistance to this wire. So I physically raise this up, but when the electrons move, when they're moving through there, they're forcing it back down. But I can, if I wasn't able to overcome that resistant force, I wouldn't be able to move the wire and we wouldn't be able to get electricity. So we're easily able to move current or move the wire through the magnetic field, but there's a resistance. And the resistance is very important. It's the idea that you can't get energy from nothing. I can't produce this electrical energy purely just without resistance. If I could, then we'd have perpetual energy. If I could produce from electrical energy, I produce kinetic energy, and then from kinetic energy, I could produce electrical energy, just free back and forth with no resistance whatsoever. I would have free energy. It would be awesome. It would be great, but that doesn't happen. There's this resistance. So I can't just create energy from nothing, right? So that's the case there. That's what we call Lenz's law. We're going to deal with that one more in the next video as well. But that's the gist of how Lenz's law works. You're just trying to resist the motion that you're causing. It's like Newton's first law. It wants to stay stationary, so it's going to resist that motion. It's going to be similar to other laws that we